Hello everyone, my name is Brian and this is the Math 21 review video for implicit differentiation and derivatives of exponential and logarithmic functions. So let's start. Let's recall implicit differentiation first. And explicit functions are given in terms of the independent variable, usually x. But implicit functions, on the other hand, are usually given in terms of both the independent and dependent variable, usually x and y, respectively. So for given an implicit function, we have a technique called implicit differentiation. And to do this, we remember that y is a differentiable function of the independent variable x, and that its derivative is dy over dx. We differentiate both sides of the equation using the chain rule for terms with the variable y. And lastly, we solve for dy over dx, and this will be our goal, the thing we want to obtain from implicit differentiation. Now, these three steps look a bit difficult, maybe hard to understand, but later we'll have examples and I'll try giving you tips for how to think about this process. But before that, let's recall exponential and logarithmic functions. For positive a, which is not equal to 1, this one's a restriction that we need to impose when we define these functions. We define the exponential function with base a as this one, and the logarithmic function with base a as this one. And the logarithmic is the inverse of the exponential function, which we'll see in this theorem. For the given a, positive and not equal to 1, we have the following properties. These two, number 2 and 3, these are the important properties of log and exponential. They tell you that both of them are inverses of each other, which means they undo the operation of the other. And if you know both of these, you can derive this one, the first identity, which tells you that y is equal to the log of x with base a if and only if x is equal to a to the power of y. To derive this, we simply do a to the y and a to the log. And using these properties, we get this. Similarly, if we take logs of both sides, log a, we get this equality. So yes, 2 and 3 are important. We also have derivatives for exponential and logarithmic functions. These have to be memorized because they'll be used often. Okay, so let's move on to problems now. Determine the points on the graph of xy equals quantity 1 minus x minus y squared, where the tangent lines are parallel to the x-axis. You may pause the video and try it yourself now. Okay, hope you tried it yourself. And now I'll be giving you the solution. So first thing we have to note is that a tangent line of the graph is parallel to the x-axis precisely when the derivative of y with respect to x is equal to 0. To visualize this, remember that our assumption is that y is a function of x. So y equals f of x for some small enough region. That will look something like this. This is the x-axis and this is the y-axis, right? So recall that the derivative is just the slope of the tangent line. So if dy equals over dx is equal to 0, then we have a tangent line parallel to the x-axis because it has slope 0. Okay. But how do we get dy over dx? We need the derivative, which we will get by implicit differentiation. We implicitly differentiate this. D over dx and d over dx. So how do we get this expression? Here we just apply the product rule. We differentiate the left factor, that's 1. Then we keep the right factor the same. And then plus, keep the left factor the same, differentiate the y factor. Remember, d over dx of y is equal to dy over dx. So that's all. For the right side, the first thing you have to apply is the chain rule, because we have an inner function here and an outer function, which is the square. So chain rule, we bring the 2 down, copy the inner function, and then we differentiate the inner function. So the derivative of this, derivative of 1 is 0, derivative of negative x is negative 1, and derivative of y is negative dy over dx. So that gives you this equation. Now, my tip for doing implicit differentiation, because this confused me before, to think of y as being f of x, so that dy over dx is equal to f prime of x. Here we're just changing the notation, but it's helpful for me. I hope it will help you also if you're having a hard time with this. So we can rewrite this one like this, because we said that y is equal to f of x. So when we differentiate d over dx, differentiate both sides, we just simply apply the regular product rule that we're familiar with. So you can apply it yourself, the familiar product rule, minus f of x, then negative 1 minus f prime of x. We obtain this expression, and you can see they're similar. Remember, dy over dx is just f prime of x, so we obtain the same answer. I just think this one is a bit helpful to think of if you think of y as being f of x explicitly. But if you're already comfortable with this kind of implicit differentiation, then by all means you can use that. But remember, when you write your solution and final answer, you have to phrase it in terms of y. So your solution should have y's and not f of x, because that's just helpful to think about, but it's not supposed to be in your solution itself. Okay, so moving on, we simplify this and we solve for dy over dx. So we were able to get dy over dx. We know that it's equal to this expression. So remember, we want dy over dx to be equal to 0. So we need 2x plus y minus 2 to be equal to 0. Also, we need this denominator to be non-zero, because we want dy over dx to be defined. So 2 minus x minus 2y, non-zero. So we need those two equations to be satisfied. Yes, it's just a restatement. Okay, so this one implies that y should be equal to 2 minus 2x. So we substitute that to the original equation. Let me just write down the original equation. Also, because we need these 3 equations to be satisfied. So it will be like solving a system of equations. We first substitute this one into that. So yes, substituting that. we obtain this expression, we simplify it, and we find that x should be equal to 1 over 3 or 1. We're not yet done. We still need to check that this equation, 2 minus x minus 2y, is not equal to 0. We need to check that this is satisfied. So straightforward, we get the y value associated with this x value, x equals 1 over 3. That y value is 4 over 3. Then we check that the expression that we want is non-zero. Similarly, we do it for x equals 1. We obtain y is equal to 0, and we also see that this expression is non-zero. So our system of equations are satisfied, and thus the points 1 over 3, 4 over 3, and 1, 0 are points on the graph of the equation where the tangent lines are parallel to the x-axis. Let's move on to problem 2. We want to find the derivative of y, which is with y equal to this expression here. You may pause the video and try it yourself. Okay. Okay, now time for the solution. When we differentiate this, for example, we want to get y prime, right? We can't simply use the power rule. We can't bring down sine 5 of x, for example, and then x squared plus 2x sine 5x minus 1. We can't do this. Why? Because this exponent is not a constant. We can only use the power rule if our exponent is a constant. Well, this is dependent on x, so we can't use it. So what we have to do, we first note that the quantity inside is positive always. Then we turn the equation into an expression with e as the base. So we insert a e here, and we also take the log. And if we do e to the ln x squared plus 2 to the x sine 5x. Recall that by the properties of log and the exponential, this is still equal to 2x to the sine 5x. And then using another property of log, we can bring this exponent down. We can make it a factor, which is what we did here. Okay. Finally, we differentiate this quantity. Here we use the chain rule. We differentiate the outer function. E to the x is always just e to the x. The derivative of e to the x is always e to the x. So it stays the same. Then we differentiate the inner function. Next, we need the power rule to differentiate this. We use the power rule. We differentiate so this is the left factor. We differentiate the left factor and keep the right factor the same, plus the left factor, which is kept the same, and then we differentiate the right factor. So we get this expression. And this is the answer to the question. We note that we can generalize this result. If y is equal to f of x to the power of g of x, then we can do the same process. We do e to the ln of f of x, and then we bring down g of x. We do it like this. Then we can also differentiate it like we did here. But do not memorize this. unless you understand how it works. I recommend you go through this process. You take the exponent, you take logs, you do all of this because you might forget this formula and you might misremember it. So it's important to know how it works. So that's all for this lesson. I hope you learned something and good luck.